Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to talk about the dimension of vector space, and then we shall look at a specific example related to that. And after that, there will be two examples related to how can you determine whether the set of a given vectors is a basis for a vector space. Okay. So basically that's all that we're going to cover in this video. Now, when you talk about a vector space, you can find the dimension of it. So here is a vector space, and you might want to ask the dimension of it. So what's the dimension? So that's a question. Now, the dimension of this vector space, well, I think it can be categorized into three categories. So the first one is we are going to have a finite dimension. So in order to know what's the dimension of it, that means you're going to have the number of vectors in a basis for V is finite, and you can count how many vectors there are in the basis. So for finite case, that means you have to count number of vectors in a basis. And it is also possible that you have the dimension is 0 if you have a 0 vector space. So that is the second category. And the last category is you might have an infinite dimension. So when you have infinite dimension, of course, it is just the opposite of finite case. So in infinite category here, that means you have no finite basis as written up here. Okay, so there you go, three categories of the dimension of vector space. And here is a specific example. Find the dimension of the vector space W. So W is defined as a symmetric matrix. Here is 2 by 2, and it has this definition where you have A and C could be different values here, but for these positions you have to have the same values, B and B. Okay, now to find the dimension of the vector space, we first need to find the basis. So you need to be able to come up with basis of W. So that's our starting point. And recall that in order for a set to be a basis, there are two conditions that you have to fulfill. The first one is that basis spans the vector space. So B spans vector space, and our vector space here is W. That's the first condition. The second condition is B must be linearly independent. Okay, now we can see that the vector space is defined as such. This is a 2 by 2 matrix. Can you come up with some sort of possible linear combination such that this is the result that you will get? Now, I can see that if I have a matrix that looks like this, in order to create A at this position, I know that I have to consider, now basically, okay, sorry, let me just rephrase. God, this is so difficult. Okay, so what I'm trying to say is, can you come up with a linear combination of something times with the first vector plus something times with the second vector and so on, such that this is the result that you will get? And in this case, we're going to have something times with a 2 by 2 matrix as well, so that you get this result. Yeah, Okay, so you will have something times this 2 by 2 matrix and so on. So we need to find this stuff here because this stuff here will be the basis of W. It can be the basis of W. So now I can see that this is the position of A. So here is the position of A. And I know that if I have something which is A times with this matrix 1 0 0 0, I can already get the position as such. A times 1 is A. Okay. But I know that I have to add with something else because here we've got B and I need to come out, or I need to create something that will give me this result. And that can be achieved if I have B. Here has to be 0 because we don't want it to interrupt the value here. So the value here is already A. A can be achieved by A times 1 plus B times 0. It has to be 0 here, or else it will spoil the result that we have already got right here. Okay, so B times 0 plus A times 1, you will get A. So that looks all right already. Therefore, in order to get B, I have to multiply this with 1. So B times 1, A times 0, you will get B. And so this position is okay, this position is okay. What about this position? I can see that in order to get the result B here, I can have the value of 1 right here. So you can see so far we have A times 0 is 0 plus B times 1 is B. So I get this result here. Now I cannot have the value of 1 because then it will spoil the result for C. So here must be 0. Okay, so B times 0 is 0, A times 0 is 0. So far we've got the result for this one is 0, not C. Therefore, we need to come up with another combination. We have C right here, where everything else is 0, 0, but here is 1. So C times 1 is C. You can see the combination A times 0, 0, B times 0, 0, C times 1, C. So you get this result. So everything is good. So based on that, you can already show that if I consider a set, we can call it set B. B is given by these 3 matrices 1 0 0 0, 0 1 1 0, and 0 0 0 1. I have already shown that B here spans vector space W. So I'm just going to like label this as 1. So if I consider B as such and consider 1, therefore I can conclude that B spans W. Okay, so to show that B spans W, you need to have a linear combination of all these vectors in set B, and this linear combination here have to result in this outlook, where this outlook here is defined as the vector space of W. Okay, so that is the first part. We have managed to show that B spans W. Now we need to move on and show that B must be linearly independent. So to show that B is linearly independent, the starting point would be okay, I don't have any space, so I'm just going to erase this part. Okay. Okay, to show that B is linearly independent, that means I need to think of, is there a combination of this such that, so here is 1 0 0 0 plus C2 0 1 1 0 plus C3 0 0 0 1. Is there such combination of C1, C2, C3 such that the result we have here is all 0? Okay, now based on that, I can continue and come up with this solution here. So C1 plus 0 plus this one times 0 is 0. So the result here is C1. Now C1 times 0 is 0. C2 times 1 is C2. C3 and 0 is 0. So the result here is going to be C2. For this one here, this and this is 0. This and this is C2 plus 0. So here is C2. Okay. And finally, C1 times 0 is 0. This one is also 0. This one and this one is C3. So this is what I've got so far. And by comparison, you can see that C1 must be equals to 0. C2 here is also 0. This is C2 is 0. And C3 is 0. So you got a trivial solution. And in this case, it shows that B is linearly independent. B is linearly independent. Therefore, B is a basis for W. So, how many vectors of B? How many vectors are there in B? So we can see that B consists of this one, B consists of this one, and this one. Okay, therefore we have 3 vectors. Because of that, the dimension of W is equal to 3. Okay, now in each case here, we have A and B. Determine whether the given set S here is a basis for this vector space defined as polynomial of degree 2. Now, we're going to start off with question A first. And if we want to determine whether it is a basis or not, again, there are 2 conditions that you have to fulfill. I'm just going to label this as part A, which is to show that does S span V. So that is what we have to show. And there is another part that we need to show, which is S linearly independent. So that's the process that you have to do in order to determine whether it can be a basis for a vector space or not. Now, what is the meaning of does S span V? Well, now to start off, we are just going to consider turning all this thing into this familiar vector notation. So what we can do is we need to determine. So for example, let me just write down here 1 plus x. If you have P2, that means you have A0 plus A1x plus A2x squared. Therefore, here is 1, x is 1, x squared is 0. So that is the first vector. For this one here, it will be 2, -1, 1. And for this one, it will be 0, 3, -2. And for this one here, it will be -1, 3, 1. Okay. So when you talk about whether S span V or not, what you need to do is you need to consider the starting point where you have a combination of all these things. Okay, so the combination of all these things, you can call it A times with 1, 1, 0 plus B 2, -1, 1 plus C 0, 3, -2 plus D -1, 3, 1 must equal to something, some values. We don't know what that value is. We can just call it X, Y, Z. Okay, you can just call it X, Y, and Z. And this whole matrices here can be written in a compact form if you consider this vector here. So 1, 1, 0, this one, 2, -1, 1, this one, 0, 3, -2, oops, and this one is -1, 3, 1. So we are writing it in this way. So here we have A, B, C, D, and here is X, Y, Z. So notice that these are the unknowns. We need to find what the values are, and because of that, we can later consider the augmented matrix and so on to solve for A, B, C, D. Okay. Now, I'm just going to call it the first equation. And let's look at the second part here. What is the starting point for the second part? Well, for the second part, to show that S is linearly independent, we're going to have the same process here where you have to consider the combination of all these 4 vectors plus B 2, -1, 1 plus C 0, 3, -2 plus D -1, 3, 1. But here the result is going to be all equal to 0 or set to be 0. And we are interested to find the value of A, B, C, and D, which we can represent similarly as such. And here we have A, B, C, D, and here is 0 vector. So again, this is also unknown, and to show that S is linearly independent, A, B, C, and D must be equal to 0. So I'm going to call this equation 2. Well, from one glance, I can see that we have 4 unknowns, and we have about 3 equations. It could be even less than that. Okay, so 3 equations or less. And because of that, I know the solutions to this unknown here will involve defining one of these as free variable, and you are going to have infinitely many solutions. When you have infinitely many solutions, then this is not going to be linearly independent anymore. Okay, so I know that the condition here is not going to be true, and because of that, I think it is easier to show that this is not true. That means I have to demonstrate that it is not linearly independent, and by that I can later on conclude that S here is not a basis. Okay, so I'm just going to consider doing part B first because of the reason that I've just mentioned to you just now. Okay, now I'm going to move on. and consider equation 2 in part B. Okay, so for that one here, to solve this, we're going to consider the augmented matrix, and it will look like this. So here we have okay, so 1 1 0 to negative 1. Okay, so here we have 1 1 0 2 negative 1 1 0 3 negative 2 negative 1 3 and 1, and here is 0 0 and 0. Okay, now what I'm going to do is I'm going to just switch the position of the third row and the second row, R3 R2. So 1 2 0 negative 1 0 0 1 negative 2 1 0 1 negative 1 3 3 0. Next, I'm going to turn this into the value of 0. So that will be R3 plus negative 1 R1. And the result here is 1 2 0 negative 1 0 0 1 negative 2 1 0. So 1 minus 1 0. Negative 1 negative 2 negative 3. 3 0 is 3. 3 plus 1 is 4. Here is 0. Okay, so next is I shall turn this into 0. So R3 plus 3 R1, R2. Okay, 3 plus 3 R2. So the result is 1 2 0 negative 1 0 0 1 negative 2 1 0. So 0 plus 0 is 0. Negative 3 plus 3 0. 3 3 minus 6 3 minus 6 negative 3. 4 plus 3 4 plus 3 is 7. This is 0. Okay, so next is turn this to be 1. Negative 1 over 3 R3. 1 2 0 negative 1 0 0 1 negative 2 1 0 0 0 1 negative 7 over 3 0. Okay, so based on this, I can see that for this one here, I have, so remember we are talking about the value of A, B, C and D. So here we have C minus 7 over 3D is equal to 0. Therefore, C is equal to 7 over 3D. That is the first equation that we can obtain. Next is this guy. So here we have B minus 2C plus D is 0. So B is 2C minus D. This is the second equation. And this guy, so here we have A plus 2B minus D is 0. A is just negative 2B plus D. This is the third equation. And as you can see, we have 3 equations, 4 unknowns. Therefore, we are going to let D is equal to T, where T can be any value, any real number. Therefore, C must be 7 over 3 T. And then B must be 2 times 7 over 3 T. minus d minus t. So that is equal to 14 over 3t minus 3 over 3t. And this is equal to 11 over 3t. Okay, and finally the value of a is negative 2, 11 over 3t plus d is equal to t. So this is negative 22 over 3t plus 3 over 3t. This is equal to, well, negative 19 over 3t. And since you can see that the solutions here are not trivial based on the solutions here. Okay, let me just erase this part. Right, so based on the solutions of A, B, C, and D, we can conclude that S is not linearly independent. We conclude that S is not linearly independent. So since condition is not fulfilled, we can say that S is not a basis for vector space defined as polynomial of degree 2. So here S is not a basis. For question A, S is not a basis, okay? Right, let's move on to try and answer question B. So I'm just going to erase the whole thing here. Okay, so for question B, again, in order to show that it is a basis, first of all, we have part A, where you need to show does S span V, and part B here is S linearly independent. So there are two things that you need to show for it to be a basis of a vector space. And following the same idea, well, you can see that I need to consider the linear combination of all this given. And so here is, for example, A, this guy here is 1, 1, 0, so that is A, plus B, for this one it is 0, 1, 1, plus C, 1, 0, 1, must equal to some values. We don't know what that value is. We can just call it X, Y, and Z. Yeah. Next, we can represent the whole thing here as a combination of these three vectors in one matrix. So we have 1, 1, 0, 0, 1, 1, 1, 0, 1. And right here are all the unknowns, A, B, and C. So these are unknowns that you need to find. And this is X, Y, and Z. This is the first equation. So that is the starting point to show that S span V, okay? Now similarly, you can also consider the combination of all these vectors. But here on the right hand side, it has to be all zeros. And here we go, we have to consider or represent everything here in this way. Again, this is the unknowns, and we have to try and show that all the values here are equal to 0 in order to conclude that S is linearly independent. Now, judging from these two parts here, part A and part B, I can see here we have three unknowns and three equations. We might be able to show that it is linearly independent, and so it doesn't matter if you want to start from part B or part A, but let's say we start with part A. Okay, therefore I'm going to consider equation 1 from part A. Okay, so in this equation, what we have is then proceed towards combining all this together in augmented matrix. So we have 1 1 0 0 1 1 1 0 1, and here is x y z. So I'm just going to change the second row with the third row, and that becomes 0 1 1 z 1 1 0 y. Okay, next what I can do is I would like to turn this value into 0, so I shall consider r3 plus negative 1 r1, and I will have 1 0 1 x 0 1 1 z. So 1 minus 1 0, so 1 and 0 is 1, 0 minus 1 negative 1, so y minus x. Now based on this, I can consider, well, turning this value into 0, and that can be achieved if I consider the process r3 plus negative 1 r2, and therefore I will get this result 0 1 1 z. So 0 minus 0 is 0, 1 minus 1 is 0, negative 1 negative 1 negative 2, y minus x minus z. Okay, right, next is I can turn this into 1, so that can be achieved if I multiply that with negative 1 over 2. So 1 0 1 x 0 1 1 z 0 0 1 y minus x minus z over negative 2. Now I can consider this part here. So what I have is here we have A, B, and C. Therefore, for this one is C is equal to y minus x minus z over negative 2, which is equal to x plus z minus y over 2. Okay, so it's the same thing. that is the value of C. Now for this one here, I have B plus C is equal to Z. B is Z minus C. So Z minus X plus Z minus Y over 2. We can see that this is Z, which is 2 over 2Z. This is negative Z over 2. So the result here is going to be Z over 2 minus X over 2 plus Y over 2. And that can be simplified as Z minus X plus Y. So I'm just going to erase. So it's just Z minus X plus Y over 2. Okay, so that's the value of B. Next is this one here. So here we have A plus C is equal to X. A is X minus C. X minus C is X plus Z minus Y over 2. And if you simplify that, you will get X minus Z plus Y over 2. So that's what you will get for that one. Okay. Now I shall just erase this part here. So based on the solutions that we have obtained, I can then write. So based on the solutions of A, B, and C, therefore we can represent the linear combination as follows. So here we have A is X minus Z plus Y over 2. So this is A multiplied with this vector, plus B is Z minus X plus Y over 2 with 0, 1, 1, plus C is X plus Z minus Y over 2 times with 1, 0, 1, and here is equal to X, Y, Z. Since this linear combination exists, then we can conclude that S here spans V. So we can conclude that S spans V. Okay. Next, so this condition is okay. So now we're going to show that this is linearly independent. And if that is so, then we can conclude S is a basis. Well, so to show that S is linearly independent, then equation 2 of part B should be considered. So we should consider equation 2 of this part, and notice that this is the same thing as considering equation 1 of part A, where values of x, y, z can be set equal to 0. Okay, so therefore what we can say that we can let x, y, z equals to 0 and consider the solutions of A, B, and C. So what is A? A is this guy here, x x minus z plus y over 2. And since we're going to let x, y, z equals to 0, this is just going to be A is equal to 0. Okay. B is z minus x plus y. And again, we just substitute the values of 0 into it. B is also equals to 0. Finally, C is x plus z minus y. And if you substitute these values as 0, the value of C here is going to be 0. Okay, so based on that, since what we have here is since we obtain these trivial solutions, therefore I can say that S is linearly independent, and the conditions here are fulfilled. Therefore, what we can say that because both conditions are fulfilled, then we can conclude that S is a basis for V. So here is S is a basis for V. Alright, I think that's all for now. Thank you very much for watching, and I'll see you in the next video.